very much, everyone, for being able to be here at the fiber sensing incubator Infoshare that we're putting on today. So good afternoon. My name is Chris Atherton. I'm the lead of the fiber sensing incubator in GÉANT 5.1. I'm joined today by Jan and Hannah, who'll be discussing different aspects. So, but firstly, just to say to you all, well, welcome. So the types of topics that we were going to cover today were to do with the use cases of fiber sensing, the technologies that we've been investigating, and also the data acquisition, data management side of things that Hannah's going to cover. And then afterwards, we can open her up. We can have a discussion about anything that you may have questions on, or if we want to continue the conversation about any of the aspects that we've discussed or not discussed. So yeah, moving on to the use cases of fiber sensing. Really, there's three bits that I want to cover. The vision that we've got, the three types of areas that we see that where fiber sensing could have a positive impact, and we'll go through some of the examples in each of those areas. What we are kind of aiming for is to develop, eventually work towards developing a service, but our vision, if anything, is to have our networks as one big sensor to be used for many different things, but yeah, to turn the infrastructure into a data generating source. That's kind of like the long-term vision, the big picture that we're trying to work towards. But there's lots of steps that we need to go through before we can get to that point. And yeah, we're only at the very beginnings of that journey. Crucially, we need to think about the use cases for that vision. There's three types of users that we've kind of foreseen with fiber sensing. These come down to security and operations of the network infrastructure, civil protection, and also scientific research. We'll go through some of those as well. So moving on to security and operations. This at the moment seems to be the hot topic that everyone's concerned about, especially since we've had a number of cable cuts in the Baltic Sea recently. For submarine cables, on average, there's about 150 to 200 submarine cable cuts per year. A large proportion of those are attributed to phishing. So it's human activity. It's not sabotage. It's just general activity that we as human beings have in the ocean. Sabotage is a very, very small proportion of those cable cuts. More of the cable cuts are caused by natural forces. So abrasion, where, say, for example, a submarine cable is exposed because the sea currents have changed or uncovered the cable. It's caused a suspension underwater, and the cable vibrates to the point where it breaks. But all of these cuts, they're not really detectable until they happen. An example I have is the Comprehensive Nuclear Test Ban Authority. Every year they go out and they survey the 100 kilometers between the land and the ocean bottom sensors that they have installed around the world. It's very expensive for them to do this, but they send a diving team down to inspect the cable to make sure that there's no suspensions. And if there are, they cover it with sandbags in order to try and make sure that the cable doesn't break, so that they're able to ensure that they can keep a track of any nuclear tests that are detectable through underwater means. With some of the cable sensing techniques, we'd be able to, in real time, keep a track on those suspensions, so we can identify them in advance, plan the work in, and prevent a cable cut or a disruption from occurring. But these disruptions, they have an impact on us as network operators. We've got to make sure that our networks are able and resilient enough to be able to cope with traffic being rerouted around the networks. It also causes delays to some of the planned work that we have, as we've got to respond to emergencies where we need to put in other diverse routes to try and shore things up if a cable cut happens in the long term. So sometimes it takes weeks for the cables to be repaired, and that has an operational impact on what we do. But that's just on submarine. Terrestrially, there's not really a good source of data about terrestrial cable cuts. We are aware of things like during the Olympics, the cables were cut around Paris. But yeah, there's no real public data source on this, and so it's difficult to say just how many cable cuts happen. But anecdotally, a lot of the cables are cut through building works or farming. We can use fiber sensing as a means to identify risks, notify cable operators, and to prevent cable cuts. And that's kind of one of the main aspects of fiber sensing that we think is a good solid use case for this technology. It's because we're able to detect if someone is coming near the cable, but also if someone's digging near the cable as well. One of the examples I have is with this is from Svalbard. So all of this is publicly available information. Put the link in the slides. But one of the cables up in Svalbard was cut back in 2022. There was a Russian trawler that went back and forth over the cable 107 times. And the cable, which was buried 2 meters deep, was exposed and then like sliced. And there's a picture there of just how damaged the cable was. Unfortunately, the authorities had to drop the investigation because they didn't have enough evidence that it was that particular vessel which cut the cable. This is because there was a lot of trawling going on in the area at the time. There were a number of vessels which crossed over the cable path, all of them Russian, by the way, but it wasn't a specific vessel that they were able to attribute the cut to, even though they have strong suspicions that it was a particular vessel that did it. It's believed that if we had information from fiber sensing, that could have played a part in the evidence gathering for making to be able to continue the charging of that vessel with the cut of the cable. But as things stand, there wasn't enough evidence to do that. We think, again, this is a potential area where cable sensing could really play a part with being able to gather evidence or impacts on the cable and feed that back to the authorities when they need it. Moving on to one of the other areas, this is more on civil protection. So yeah, there's a huge risk from tsunamis around the world. We don't know when the tsunami is going to occur, and so there's tsunami monitoring buoys deployed throughout the world. Just to give you an example, this was an image I took it was about a month ago, but there's online sources where you can find this. All of the red dots are the tsunami monitoring buoys which are turned off or disabled. And these are in areas which, yeah, need to protect human life. The image on the right-hand side is, it was the tsunami that occurred in the 1700s off the coast of Portugal, which severely damaged, killed a lot of people at the time, but severely damaged all of the infrastructure in Portugal. And just to give an idea of the impact of, well, not the impact, but the potential of a tsunami, the Indian Ocean tsunami, which happened in 2004, the previous largest tsunami that occurred before that was in the 1600s. So there's no real link between the time from one tsunami to another. It can happen at any time. The consequences can be devastating. Lots of people can be injured. With the type of system that we're looking to deploy, we're not looking to do this type of work ourselves. We're not looking to do the research or to identify tsunamis. What we're looking to do is to make the data available so that other people can do that. People that have the skills, that have the knowledge to be able to use this information in their existing workflows and processes that they have. The way that they typically work with tsunami monitoring at the moment is using the tsunami monitoring buoys, but these are typically moored off the coast of populated areas, like obviously, but that means that fishermen can come along, use them as mooring points and damage them, and that's what's happened in Indonesia, where the 22 buoys that were deployed after the Indian Ocean tsunami there, only 1 or 2 are currently working. All of the others have been switched off, mainly because it's so expensive to keep those systems running. What is in place, though, that has a clear global footprint is the submarine telecoms cables that we've got access to. So it's not just the cables on land which can be used for monitoring, it's the submarine cables that can be used for monitoring the Earth and its functions as well. With that is obviously earthquake monitoring. I've got here a couple of images. One of them is the submarine cable between Crotone in Italy and Preveza in Greece. This is part of the GÉANT backbone network, and it's currently being looked at as potentially a place where we can deploy fiber sensing technologies on this cable. Just by there is a huge fault line that runs up the coast of Greece going towards Albania. And there's a number of parts of that fault line which are completely unbroken at the moment. And those unbroken parts present a risk for a huge earthquake. And right now there's a problem that they have in that they can't accurately map where the fault line is as it goes up the coast. The reason for that is all of the seismic stations that they have available are based on land, and they've not really got anything at sea to do the active seismic monitoring. If something is deployed, it's normally on a short-term basis. This is an issue because in order to try and localize the epicenter of where an earthquake is, you need to use a technique called back projection. And because there's no seismic stations in the water, they're not able to truly localize the exact place where the epicenter is. And so you get this swimming artifact effect, which means that the location moves around a particular spot. And this is what's happening now in Greece. So in order to try and make sure that there's enough resources and warning available for potential huge earthquakes in the region, they need to be over prepared, which can sometimes lead to people not taking notice of warnings, but also from a government perspective, if it's seen that particular fault is at risk of causing a huge earthquake, then a government can then put in place the necessary resources or infrastructure in advance in preparation for an earthquake, a large earthquake happening. That's one aspect of earthquake monitoring. The other aspect of civil protection with an earthquake monitoring is to do with the building regulations themselves. So especially in areas where there's a high seismic risk, there is the International Code Council, the ICC. They have building code standards for buildings in high-risk areas where there's risk of seismic activity. And the construction of buildings in those areas is determined, or like the underlying design principles are determined by the risk factors for earthquakes occurring. And without knowing fully what the risk factors are, buildings can get over-engineered or under-engineered, depending on how little or much information they have available or is known about the risk factors. So several seismic institutes who NRENs already serve, they define the seismic provisions within the building regulations in their respective countries. Again, this potential use case for us to supply information to them, or rather data to them, and they can turn that into the information or the derived products that they need in order to make a better informed judgment for the different types of work that they have. The scientific research side of things is a lot easier for us to discuss. We've been able to detect earthquakes with fiber sensing techniques. There's a massive amount of examples of this now, especially in the last few years. There's been a more or less an exponential increase in the amount of papers coming out that reference this type of technique using DAS with seismic sensing.
Yeah.
We've been with some of the cables where we've deployed sensing technology. We've been able to find earthquakes like very close, but also very far away. We've also been able to monitor the oceans and oceanographic effects. So here is like one image I've used a few times. In the center, there's a number of bands from frequencies which were detected over 21 days. And it's very low frequency wavelength pressure waves that are coming through the water. And we were able to detect, or not we, but the research groups that have this data were able to detect a storm off the coast of Brazil, 13,000 kilometers away from where the interrogator was based, which is up here in Svalbard. And this is where the storm was, off the coast of Brazil. So this type of technology has got the potential to monitor the Earth's oceans as well as the movements of the land. And then, the other case that we have for like certainly on an ocean, the ocean side of things, is with marine biology, which I've got a recording here of one of the whales that was picked up in Svalbard, which I'm hoping you can hear now, but might not be able to. But if you do get the slides, you can listen to it. But this was a whale that was feeding in the fjords around Svalbard.
We can hear us, Chris.
You can? Oh, perfect, thanks. So yeah, there's lots of different use cases for fiber sensing. Not one of the usual suspects is with traffic monitoring, where in fact it was Donal and a bunch of researchers in Ireland were recently able to pick up traffic moving up and down a road next to the building where the DAS was installed, using that to try and track speed of vehicles, locations of vehicles, and yeah, numbers of vehicles. That's of interest to many different research groups. I've put sociology here, but there's different types of use cases for this. And especially like with applied sciences, with the likes of monitoring trains for catenary flashovers, which is where if a tree branch gets too close to the overhead rails, it creates a brief but distinctive sound, and that eventually leads to a fault with the overhead rail system, which I experienced myself earlier this week when my train got cancelled because there was a fault on the line with a branch that had got too close to the overhead rails. So this is not something that's like make believe. This does actually happen on a daily basis around Europe as well. But this technology has the ability to kind of detect these events which are happening in real time. It's the means of getting that data or extracting the meaningful information from the data, which is the challenge. And I think Hannah's going to talk about that later on. But now what I'll do is pass this over to Jan, who's going to talk about the technologies. So Jan, over to you.
Okay, thank you. Okay, so now I'm going to talk about basic principles and technologies for fiber sensing. Just these slides were prepared by me and my colleagues. You can see all of them. Next, please. Very short outline. I'm going to talk briefly about history of fiber sensing, about basic principles, then what is important, fiber sensors classification, and I believe the last point is very important for NRENs and GÉANT, real and practical deployment. Next, please. Fiber is studied for a long time, especially for the sensing application for 1960s. Standard telco fibers, which we use, is made of silica, which is silicon dioxide, with certain dopants. And when this fiber exposed to some external effects, we can push it and press it, perhaps hit it, then these molecules move, and we can detect these small changes in positions when we use light as a probe. Okay, then, no, please, not yet, sorry. We can monitor and measure amplitude, frequency, phase, or polarization. Not all of these properties are changed at the same time, and also we can detect them with certain apparatus only. Sometimes we hear hot debates about cable sensing and fiber sensing. We can tell that the real sensor is fiber, not optical cable, of course. Next, please. Fiber is very tiny. We can think about it like human hair. So we can let's try to imagine another type of sensor. Let's talk about any metal tube or bar or even string. And when this tube or piece of steel is hit by the hammer on one end, we can hear and even feel the disturbances along this tube. So we can use human detectors, of course, ears, but we are quite limited. We could use better ears or better electronics. And that's this principle, what we do with glass tubes or bars, which means fiber. Next, please. Okay, basic principles. We can have this metal bar as a sensor. You can see these metal bars. When we hit some of them with a hammer, we can hear it and feel it. With human ears, we can detect something 20 hertz to 20 kilohertz. It's just very, very dependent. Certainly, I cannot hear this range. We could use bats for very, very high frequencies or some electronics. As Chris said, with DAS sensing and fiber sensing, we are interested in rather low frequencies. Next, please. Now, this is glass bar as a sensor. Of course, this is sort of joke or hyperbole, because definitely we do not want to use this glass bar as a sensor. Also, we do not use hammers. We use a source as probe lasers, and we do not use ears, but photodetectors. These photodetectors can be located on the same end of the fiber as laser, then it's called DAS, or on the opposite, and then we talk about state of polarization or polarimetry. This is quite not so difficult part. Of course, data storage, analysis, it is much more difficult. Okay, next please. Distributed sensors are used frequently because there is no other element which is definitely needed for sensing, and it means cost reduction quite big. Two basic techniques which can be used are OTDR, which is optical time domain reflectometry, and SOP state of polarization. In fiber industry, this traditional OTDR is well known for the last, 30, 40 years, and is used very frequently to check whether your fiber is okay or not. For fiber sensing, we do use advanced principles, but the basic principles is just OTDR. Next, please. Okay. Here just a few pictures from Chris. DAS uses reflections from impurities, or not perhaps from impurities, for any molecule in the fiber. When laser hits them, there is just something which is called scattering. On the left-hand side, we see 3 arrows. On the opposite, only 1 arrow. This is just indication of attenuation of fiber, because some energy or some photons are scattered or lost. And state of polarization uses changes in the polarization of this laser light. On this left-hand side, this arrow is something which we call horizontal polarization, and then we go through the fiber, and on the right-hand side, it's just horizontal polarization. There is also, we know polarization, there is polarization sunglasses, because light from sun is highly unpolarized, and when this goes through these sunglasses, we see only one polarization, so any reflections or glares are highly suppressed. On the other hand, laser is highly polarized, so we can tell that something is going on in the fiber with better accuracy. Next, please. This is just basic principle of OTDR, using or utilizing something which we call Rayleigh scattering. So we have laser source, thus this light is injected into fiber, and what is coming out of the fiber is then fed to photodetector, and then with some electronics, we have OTDR traces. Of course, real OTDRs have much more components. This is very, very basic. There are also other scattering processes. We can mention Brillouin scattering and Raman scattering, but these methods are used less frequently because these Brillouin and Raman effects are weaker. So it's more difficult to get enough light just to work with them. And this traditional scheme, OTDR, or method, has been improved, and now we have so-called phase-sensitive or Phi OTDR, phase-sensitive or coherent methods for DAS. The main difference that not only amplitude but also phase are evaluated, and also the trick or what is necessary is better laser on this laser source. Next, please. Here is just OTDR measurement. On the left-hand side, we have distance and power. So we can basically check whether our fiber is okay, because less and less photons are coming back to our detector. So this curve going down in this direction, and on this, there is just some noise. When we compare it to DAS or phase OTDR, because of better laser and better analyzation, this would be much more detailed curve, but can be difficult to read for humans. So next slide, please. We have something which is called waterfall. Here you can see two different DAS results. They can be displayed as OTDR, but this waterfall is much more, I would say it's a really nice visualization. There is distance versus frequency or strain. Here you can see shape, so basically just very, very few basic frequencies. And with whales singing, it's just this picture is sort of blurry or fuzzy because a whale or humans can produce more frequencies, and this is the basic difference. Here you can see when something is in this blue color, the strain is not so strong. When something is really stronger and stronger, it's just these green and yellow colors. Next, please. Oh, okay, here should be something perhaps. Oh, okay, thank you, Chris. We can see not really live data from Blue Lagoon on Iceland, but this was pre-recorded. You can check this on YouTube. That horizontal axis is time, vertical axis distance. And again, colors are proportional to the strength. So basically, more movement, more shaking, more tsunami. It means more deformations and then more intense and different colors. Okay, thanks. Next. All these OTDRs methods can be perhaps described as single-ended. So it means that source of the signal, which is laser, and detector are placed in the same instrument. State of polarization is different. We have laser source, fiber, and polarimeter is located on the opposite side of the fiber. In this case, we can use any signal transmitted in fiber, can be data signals or some optical supervisory signals, which are just used for basic communication between equipment, and we can use polarimeter. Okay, this is just different picture than with OTDR, because state of polarization just describing how the vector of the electric field behaves. It can be tricky a little bit, at least for me. And we have this linear, horizontal, vertical polarization. Then we can have circular and elliptical. It can rotate this vector clockwise, counterclockwise. And the results, again, can be displayed on something which we call Poincaré sphere. And you do not see these circular or elliptical curves. You will see different points. And on this picture, every point is representing certain polarization. Difference between red and blue, that red is just the front side of the sphere, and the blue is back side of the sphere. And we can see this picture, fiber would be quite okay. Nobody is playing with it. And the second picture, you can see very, very wild movement. This is just static picture, but in reality, you would see this very, very dynamic behavior. Next, please. We can perhaps say something about advantages and disadvantages. State of polarization is rather easy to implement, and there is cost effective because there is no need for so high quality lasers, which are of course expensive. We can cover long distances, hundreds of kilometers. We can go through optical amplifiers. Localization of events along the fiber is not possible in this basic setup. When we use two signals with different wavelengths or colors, this event location problem can be improved. Because different wavelengths travel at different speed, it's just rainbow. This effect is called chromatic dispersion. And then we can calculate the distance where something happened. Of course, also we can use two wavelengths which are spaced enough or close together. Again, when we do use time stamping, for example, with use of White Rabbit technology for precise time stamping. Next, please. DAS. Distributed acoustic sensing is de facto standard because localization of events is very, very good. On the other hand, distance is limited as with any OTDR because amplifiers will block it. Of course, you can find perhaps some special schemes, but just normal DAS have limited distance, perhaps up to 100 kilometers or less. Of course, we have these high quality lasers and therefore perhaps slight disadvantage would be higher price. And also here we can see what I said on perhaps on the first or second slide. We are really interested in very, very low frequencies. You can see perhaps, I hope you can see it, distant storms. It's well below 1 hertz, earthquakes, and then we have these whales and perhaps ships. We are definitely not interested in 20 kilohertz or anything like that, or as far as I know. Next, please. I would say this is really important practical deployment. As far as I know, that in NRENs and GÉANT fiber networks, we have two different fiber sensors. One is DAS, based on OTDR, with reach limited but de facto standard, and then state of polarization. These days, we are using external polarimeters, but your digital high-speed coherent receivers can also work with state of polarization. So we will see what perhaps in next few years, these digital coherent receivers will be also used as state of polarization detectors. Also, we can say that there are also other methods, for example, interferometry, but this method is not so widespread because you really need very, very good laser. And even this method was here before DAS. It's definitely used only in few fiber networks because it is one thing you can build your interferometer and you can try to measure speed of light, which was done more than 100 years ago. But just to use interferometry for definitely fiber sensing, you need time and frequency networks. Again, precise time stamping is very, very important. Without it, it cannot be used for sensing. Okay, next, please. And this is also last but not least, sensing can be used together with data transmission. All signals, of course, now I mean data, signals, and sensing can be transmitted in one fiber because fiber is quite expensive. We can use different multiplexing techniques like dense WDM technologies or coarse WDM technologies. What perhaps can be say, polarimetry can be deployed without any problems because even we can use these optical supervisory channels. DAS may interfere with your data because you are injecting something in your fiber, but it's definitely doable. I would say that everything what I was talking about is relatively easy, but the biggest problem is how to discover and find the useful signal in all of the noise, because then we can try perhaps to be proactive and just to do something before fiber is really cut. And this is much more difficult because huge amount of data are produced, and more on this later. Next, please. If anybody is interested, I try to find free resources, no login required. The first one is really nice animation for a state of polarization. Then these one or two resources, perhaps more technical, but again, quite good. Again, this nature, I use this nice picture. And the last one, Subtle Forum, is just using submarine cables for tsunami warning, and it's interesting because this is an article from Infinera, which is used in GÉANT network. Next, please. Thank you very much.
Thanks very much, Jan. So now we've heard about the potential use cases. We've also heard about the technology that goes behind that. But now we're going to go over to Hannah, who's going to talk about the difficulty that both myself and Jan have spoken about with finding the signal and the noise.
Yes, thanks for the introduction. As Chris said, my name is Hannah, and I work for DeiC, which is the Danish NREN, as a data management consultant. I have prepared an agenda. We're talking first a little bit about an introduction. So how does data management connect to fiber sensing? The ecosystem of fiber sensing, and then the stakeholders. And we need these first 3 steps to actually get to the data acquisition. We start with the introduction. I know, very creative. I want to say first a couple of words on the terminology. So although we talk about fiber sensing, fibers are normally a part of a multi-core cable, which you can see here. They are coming out of the big cable. And changes in the environment of the cable can be detected using the fibers within the cable. So just these small things that come out here. The level of access granted is to a dark fiber, meaning that it is not used for telecoms traffic or anything else, where we can use any frequency we want. You could see in the talks before that different frequencies show us different things in the environment. However, maybe sometimes we also get access to a part of a shared spectrum where we are allowed to use only a specific set of frequencies as the fiber is shared with other organizations or projects, or like other stuff is happening there. Just as a disclaimer, although the same principles apply to subsea and terrestrial cables, my viewpoint might show a focus on subsea data because I'm also involved in the Submerged project, which is only focusing on subsea cables. But the amount of data that can be collected from a fiber is significant. I will show an example on the next slide from the Submerged project to give you an overview on what, orders of magnitude we're talking here. In this data that we're collecting, there is a lot of noise mixed into the data we're interested in. But sometimes you can derive a lot of data from what other people consider noise. Like if we're talking about the different use cases, they are not all going to be interested in the same kind of data. And we can't share the raw data from our fiber sensors just freely, depending on the country that is involved, so where the cable is lying. You may have to get a clearance from military or other national security agencies to release the data. And you may only be able to share processed data at all. And some data is just more sensitive than others. What we can do is give access to selected researchers or other people interested that might go through a vetting process and then can access the data in a so-called trusted research environment. And then on top of that, we have involvement of different research areas that all have their own standards and metadata formats. So we need to make sure that they can access the data in a way that they can produce that themselves, or we give that to them in the right format. And because I'm a data management consultant, I need to say that, but we want fair data. I don't know entirely what my audience is here, but FAIR stands for findable, accessible, interoperable, and reusable. And that just means it's a fancy acronym for saying we want that our data can be accessed by others. It needs to be able to be found And we can reuse data, so we don't need to produce the same data over and over and over again and pay a lot of money for reproducing data. FAIR has nothing to do with open data, so also our data is quite sensitive and sometimes very restricted. We still want that our data has the right amount of metadata attached to it, and it is clear if we're allowed to access the data how we can do that. And here is an example from the Submerged project. This is from Svalbard. I mean, as you can see, like there's kind of large ranges, so it is not straightforward to say how much storage we need. In the tests that have been carried out on Svalbard, there have been retrieved 3 to 7 terabytes in one day from one DAS unit, and 6 to 12 gigabytes in one day from an SOP unit. There are certain things that can be done to reduce the data volume, like we can exclude certain channels or frequencies, we can have larger spatial and time resolutions. So the exact amount of data collected during the day depends. And this does not include yet the storage of the FAIR data that is then lying in archives. You're going to understand this probably a bit better later, when we're now starting to talk about the ecosystem. This is a super nice picture, I think. It's not made by me, it's done by my colleague René Belche, who's also involved in the Submerged project, and he took the time to visualize all the different components that are involved in fiber sensing. We start with an interrogator on the cable on the left, and we go through all these different steps and then end up in throwing out data. This looks super simple, right? So we don't need to talk much more about that. Yeah, unfortunately, it's very complicated and complex. We have to make a lot of different people happy and comply with a lot of rules from different stakeholders. And what we're going to do in the rest of my talk is that we're going through this ecosystem step by step, first from a stakeholder perspective and then from a data acquisition perspective. So we start with the stakeholders, and there's a lot of them, and everybody knows when there's a lot of people with different opinions, there's a lot of chaos. We start with the fiber infrastructure owners. So the hardware, specifically the cable, belongs to these fiber infrastructure owners. They might also be owner of the interrogator, or they have allowed other stakeholders to install one on a fiber. That could be an NREN, that could be somebody else that has money to buy a DAS unit. And the data that is produced or like captured by the interrogator can be owned by several different people, depending on the contracts made with the fiber infrastructure owners. So do the infrastructure owners are the owners of the data as well? Is it the NRENs? Is it the researchers, or is it someone else? And this all depends. I know it's at least the 5th time that I say it all depends. This is all up to contracts and agreements made beforehand. Then we have the data users. We have now the raw data from an interrogator. So who is allowed to look at that? And again, it depends. Some countries may require researchers to handle raw DAS and SOP data to be security vetted, which is shown in the ecosystem diagram by this barbed wire around the secure HPC and data center. They may store the raw data in secure repositories or process and filter the data and then store that in a repository. You can see that different people there, and researchers from different research areas, like for example seismology, oceanography, or marine biology, might all have their own repositories where the data is stored in the discipline-specific file formats and with the discipline-specific metadata attached to it. Then what Chris also talked about, the data could pass through the hands of different civil groups like early warning agencies or the military or state intelligence and law enforcement, or it might be used in commercial infrastructures, like railway operators could be interested in that failure before the stuff actually breaks, so that tracks for trains can be replaced on time before an accident happens. And then finally, the data, either raw or processed, makes its way outside of the barbed wire and into the hands of researchers who do not need to be security vetted. That's what you can see then here on the outside. We have also like a big group which causes us a lot of headache, which are the policymakers. And what policymakers we need to look at depends again. It can just be a regional issue when data is collected on a short, dark terrestrial fiber that is located only in one country. That might be very straightforward, or it can be really, really complex, as you can see in the picture here on the left side, where we're looking at the Medusa submarine cable system. This cable system connects the Mediterranean Sea, the Atlantic, and the Red Sea, and it drops off in multiple countries and continents. This means that we have a lot of different national agencies, like national security agencies or NRENs, and different research organizations that have their own opinions on data acquisition practices. And just to show this, like the policymakers are influencing the entire ecosystem. And these opinions should be getting organized in a policy framework. And yeah, it's so many different like people and people that are used to work differently with different viewpoints. So for example, does the United Nations Convention on the Law of the Sea apply? Are the cables all in the same legal jurisdiction? They probably pass from one country to another if they are subsea, starting in country A, passing through international waters, finally terminating in country B. Are you required to get clearance from national security agencies in any of these countries? Does your organization have policies of its own? These are all very, very good questions that need to be answered by the involved parties, while keeping in mind that the data still needs to be in a form that makes research possible. This means processes for data access can't be too complicated for the individual researcher, and data can't be filtered in a way that makes it useless for researchers just because national security agencies are way too cautious about it. And now we have a look at the same picture again, just from a different viewpoint, from the data acquisition perspective. We start again right in the front at the cable. This cable is installed. An interrogator is installed on one pair of fibers in the cable, and then the data is sent back to a central location, normally a secure data center, as per local laws and policies, as we have already talked about. And then it goes from there into a raw data buffer. The raw data is usually held in the buffer for a fixed period, because otherwise the storage costs would be just tremendously high. And the size of the storage may indicate the length of the period that we can store the raw data for. As we said earlier, like 3 to 7 terabytes per day and interrogator is not that unusual. It's maybe the upper limit, but it's not unusual. And just in case you're too lazy to do the math yourself, 7 terabytes per day equals 630 terabytes for 3 months, just for one single DAS unit. We can then, if we have different interrogators, we might call this a federated infrastructure, where data users have access to several incoming data streams from different locations, collected in different secure environments. And these two data streams can be merged if that's necessary for what I want to figure out. You can merge the data streams inside the secure data center, which can be necessary for matters of national security and can only be done if both interrogators are in the same country. Most likely, again, it all depends. And you can also merge the data streams outside of the secure data center that can give useful information on the big global pictures like earthquakes or ocean streams. So this is very interesting for researchers. We need to pre-process our data. The sheer volume of sensor data means that it must be processed using automated filters. This also means that certain events need to be labeled by hand, so we can feed algorithms with them, that these algorithms learn what a specific event looks like and can then do it themselves. As a part of the process, sensitive data may be scrubbed from the stream. That can be military vessels passing over or something like submarine cable cuts that we might not want to make public right away. And data which seem to correlate with certain events, like just regular ships or whales passing over the cable or earthquakes, can be labeled directly and then sent to a repository. We have already looked at this picture in Jan's presentation, which is an example frequency domain plot, where you can see 10 seconds worth of data. This specific file is 420 megabytes big, so just for 10 seconds worth of data. And this specific one has already been through some processing where strain rate has been transferred to a frequency domain. And you can see these horizontal lines in there. And if you know stuff about this type of data, then you can see from that this is a ship. If we can help our algorithms understand that themselves, then algorithms can label this, and we don't have to look at every single 10-second file and identify that ourselves, that, oh, here are horizontal lines, this is probably a ship. We need to save this data. Once that anyone has considered it as interesting and important enough, we need to send it to repositories or archives. We might need different ones for different disciplines, because researchers like to go where they always go to find their data. Ideally, we want to have this data stored in open formats so that data can be shared where possible and with discipline-specific metadata attached to it. So you don't need to download huge amounts of to you completely useless data. Like if I'm only interested in whales, then I only want to download the files that have information on whales in them and not ships or cable cuts or something like that. This data that is lying in the repositories might still be sensitive and should be protected accordingly, for example, by limiting access rights to certain research groups, for example. The repositories here at the top contain data extracted very early in the data pipeline. Repositories 3 and 4 here at the end are outside of the secure data center and are the last chance to save the data before it's deleted. And we talked about data deletion. This is sad, of course, but unfortunately, we never know what we don't know yet. There might be some useful information in the data, but I've also told you how much data we're producing. And we just can't save all of it. but storage costs money, so we have to throw it out. And I leave you with that.